Quick methods of computing mean, variance, CDF, naturally standard deviation of uniform probability distribution, that is with a PDF that is highlighted here, is discussed in this example. Okay, so as you can see, the f of x, small letter f of x, PDF, probability density function, is valid here because obviously the area, which is the most important test, turn out to be equal to 1 as expected. So the area, because we have just a simple uniform distribution, the height, which is 1 over b minus a, times the width, which is b minus a, is obviously 1. So everything is all right. Now let's go back to computing mean. So expected value of x, which is the mean, is, or average, is equal to integral the full range for random variable x on the x-axis from a to b, and x times f of x dx. And obviously you can see that since f of x is constant, therefore we can substitute f of x with 1 over b minus a, and it's a constant, we can push it behind the integral. So 1 over a to b, so integral from a to b, and then we have x dx, which simply becomes 1 over 2 times b minus a x squared, and then from a to b. And obviously this integral is simply is computed to be 1 over 2b minus a, and then once substituting x with b, so it becomes b squared minus a squared, which is simply b minus a times b plus a divided by 2 times b minus a, which become a plus b divided by 2, which is exactly as intuitively expected as well. So that is expected value or mean. Basically, we are confirming as expected that the mean should be in exactly in the midway between a and b. So a is the starting or the lower threshold for the random variable x that is uniformly distributed, and b is the upper threshold. And as this confirmed, the mean for the uniformly distributed random variable is exactly midway between a and b. Now, the variance. So next step is computing the variance, and you can see that the variance of x, also known as sigma square for random variable x, is simply again integral the full range a to b, this time x minus mu. So by definition, variance of the weighted average squared deviation of a random variable from its average, or mu. What we computed here is mean, or mu. Mu is equal to expected value is equal to this, which is as was obtained. Mu is, or average or expected value, is this much. But let's not substitute for mu. So and then we have to do a weighted average of the squared deviation from the mu by the probability as shown here. Okay, but we know that we are talking about uniform distribution, so f of x is simply this constant as we just talked about. So since it is constant, I am going to apply that. So therefore variance of x is simply integral from a to b, and f of x is 1 over b minus a. I can push it behind the integral, so 1 over b minus a, integral from a to b, and this time x minus mu squared dx. But mu is a constant as we computed, so therefore this integral just simply become 1 over 3 times b minus a, and x minus mu cube from a to b. Okay, so the last step here is just substitute. So we will get, once substituting x with b minus mu cube minus a minus mu cube divided by 3 times b minus a. Now, the last step is, if I substitute now, is a good time to substitute mu with the value we found in step 1. So it become b minus a plus b divided by 2 cube minus a, so minus a minus a plus b divided by 2, and then cube the whole thing divided by 3 times b minus a. So is equal to, okay, if we reshuffle things around inside each those, let's say, component in numerator, we end up with these values. We end up with b minus a divided by 2 cubed, and then minus a minus b divided by 2 cubed, and the whole thing divided by 3b minus a. Okay, we have the denominator 2 in numerator to the power 3, so I can just do it this way. It become 8, and then I can write 1 over 24 b minus a, and then we have b minus a cube minus a minus b cube, which effectively become 2 times b minus a cube, because it's an odd power. So we can push the negative sign or negation to inside of the odd power. As a result, we get, you can see that we get b minus a squared, because 1 power is removed by the b minus a in denominator, cancel out that one, and then 12 in denominator. So that's it. That is the variance, or sigma square, of uniformly distributed random variable that is computed here. And the nice thing is standard deviation, naturally, which is sigma x, is just a square root of variation. Therefore, so square root of variation. Therefore, we get it to be a square root of what we found here, which is b minus a divided by square root of 12. Okay, the uniformly distributed random variable and these standard deviation and mean and variance has a lot of practical application in, say, quantization, noise analysis, in communication system, digital signal processing, and many other applications. So there are many practical use cases for these things. Now, the last thing I want to do is the CDF, as I mentioned. For CDF, it's just, let me just remove what I showed here in terms of the area under the under the PDF. So CDF is simply when you say you have, let's say, so I'm going to remove the a plus b at the center, but let's say you have a specific value of x here. That's what you are interested. So x can be any value between a and b, but let's say this is a specific value, and then what you are interested in is, hey, what is the probability that x is between a and x value? So basically you're trying to answer this question in CDF. You are trying to say that when you are computing CDF, or cumulative density function, for the case of continuous random variable, it's capital F, not a small letter f, capital F x x, which means the probability that your random variable, is greater than the minimum, but less than the target. So random variable less than the target specific value of x that is shown there. Okay. And of course, in this case, it's easy because it's just that red dashed area under the PDF, which is not hard to compute. You can see, but effectively, it is just simply in general an integral of PDF. So integral from a to x, let's say a small letter f, just a substitute variable, dv, and then in that case, because again the small letter f PDF is just 1 over b minus a, it is pushed behind the integral a to x, and then dv, which obviously exactly as we expected, it become x minus a divided by b minus a. So x minus a divided by b minus a, which is exactly what we visually expected, because x minus a is the width of that triangle, of that rectangle, and then 1 over b minus a is the height, so that's exactly width times height to give the area. So effectively what you see, if I move this to maybe I move this portion to here, and then I can graphically show you what I mean. So the CDF, so the CDF looks like this. This is again X, and of course, as before, you only start from the minimum allowed, which is A, and you can go up to B, of course, nothing more. But then, as you can see, at A, when you try to, for example, compute what is F or CDF at A, naturally you just substitute X with A, and when you do that, you can see that numerator becomes 0 as expected, so it becomes 0. So you are, if this is CDF or capital letter F on the y-axis, at this point you are crossing, so it's A. And then, of course, when you get to B, when X is equal to max allowed value, which is equal to B on the x-axis, it just the whole area under the distribution. So what you expect is when you hit this point, so what you expect is when you hit this point, you should the line for CDF should reach value of 1. So this point, okay, let me just write the CDF here. Okay, so this point should get to 1. And the tangent, as you can see, is 1 over B minus A. And of course, the intercept, if you could go below A just to visually show the intercept, which we can't, so then the intercept would be the value that is minus A divided by B minus A. So it would be just minus A divided by B minus A. That's the y-intercept. So the CDF is effectively a line with a formula that is just shown here for the uniformly distributed random variable. I hope that this example and this computation is helpful to remember and recall how mean, variance, and then standard deviation and CDF for uniformly distributed random variable is computed and used.